Ladies and gentlemen, welcome for all. We have the second lecture of an advanced procedure for design and sizing of a grid solar photovoltaic system using manual calculations and simulation. As we said before, we have a case study of 4.5 kilowatt peak power. Okay, in order to facilitate this lecture, I divided the main lecture to 4 parts in order to understand each section and the total content of the subject. Okay. The learning objective of this lecture, the first one is how we calculate the load calculation, and we will discuss the expected losses in off-grid photovoltaic system and the overall DC to AC derate factors, and we will also calculate the adjusted total daily energy required, and the fifth section, how we can design the inverter or inverter sizing. Okay. At the first section, we will discuss the load calculation. This table represents the appliances in a specified home. As we see, the appliances, fluorescent lamps, ceiling fans, TV, refrigerator, computer or laptop, water pump, vacuum, and the freezer. And this, the second column represents the number of appliances or pieces, and the third column represents the power of each appliances, and the fourth column represents rated running power for each type of appliances and watt, and the fifth column represents the operation time in hour per day for each type of appliances, and the sixth column represents the energy demand in watt hour per day, and the sixth column represents the third power for the specified appliances. As we know, the motorized appliances such as the refrigerator, water pump, vacuum, or freezer must have enough starting current, which is called surge current or surge power, for a very short time, maybe continue for 20 seconds, 15 seconds, or even 30 seconds. This value represents the summation of additional surge power for the ceiling fans, refrigerator, water pump, vacuum, and the freezer. Where the maximum AC power requirement 2325 watt in normal operation. So there is a difference between the required power in normal operation with respect to the additional surge power required if we assume that the devices with induction motors will be start or operated at the same time in the worst case. Also, we see that the AC power requirement in summer months, this value, while the AC power required in winter month will be 1625 watt. Okay. And the total energy demand per each day will be 21,000 watt-hour per day. Now let us discuss the expected losses in off-grid photovoltaic system. The final output of power or energy of the system will be vary from one side to another for many factors, many parameters. The temperature represents the most effective parameter. As the temperature rising will cause the increasing of solar cell temperature will be increased also. So as if we are looking at this graph that represents the relation between the current and voltage, and this curves represent the effect of temperature. While the temperature rising from 0 Celsius to 75 Celsius. As we see, there is a decrease in voltage of modules with increasing the temperature. So this represents losses. This is very important losses and very effective losses. While with increasing the temperature, there is a decrease in power and increasing in power losses. So we will always deal with the temperature derate factor, or called also temperature losses. Also another factor, the accumulated dust on the surface of modules that we must be cleaned either manually or by machinery. And also there is a losses in DC and AC cabling or wiring losses, and this will be discussed in details in the next lectures. Also another source of losses, how we will install the systems, either on roofing or on grounding. If the roof will be inclined or flat roof, this also affect in decreasing the energy that caused by incorrect tilt angle or incorrect orientation of the photovoltaic modules. In general, the losses in the range of 25% or less, or maybe a big number or more than 30%. This is represent very large value of losses, and all these losses will cause the reduction of energy production from the photovoltaic system. If we are looking at this equation that represents the inverter efficiency, the inverter efficiency represents the relation between the power output with respect to the power input to the inverter, and this relation can be divided to between the power output divided by the power output plus the power loss. So the round trip efficiency of the battery also represent and share with the expected losses in the photovoltaic system, and typically the round trip efficiency of the battery plant may be represent in general an average of 80%, or maybe in the range of 75 to 85%, and this represents in general the typical value of the losses and battery in the process of charging and discharging. As we see, this diagram represents of a grid system that consists of PV modules, inverter, and this represents the utility, and the household generator, and this represents the battery bank, and this represents the electrical consumption by the appliances of the home. Now let us discuss the overall DC to AC derate factors. This is more details than before. As we see, this represents the impedance at optimal tilt and orientation for the PV modules, and the energy flow as 100%. Now, this flow represents the total power incident on the module, also 100%, and these on the right and on the left of this flow chart represent the sources of losses. Each source have optionally losses value. As example, incidence angle modifier IAM losses due to reflection with 200% temperature losses, as we discussed before. This value may be decreased more than 33%, may be increased according to the temperature or ambient temperature of the site. This is just optional value. Okay, also module derate and dust losses. With this value, module degradation also affect the overall losses, and also this is the effect of tilt angle and incorrect orientation will cause another source of losses, and spectral losses have another source of derating factor. Module reflections, the reflection of lights on the surface of the module will cause also another source of losses, and also global incidence in collector plane also has another effect of a derating factor. Also module mismatch between the modules, another source of losses, and this represents the summation, the net value after subtracting the percentage value of losses from these factors. And now this second block, yellow block, represents the total power of at module level with this value. Also in this stage we have another sources of losses, such as mutual shading. Shading has another effect of losses, and charging controller also another source of losses, battery losses also, and the losses inside the inverter from DC to AC. Also we have wiring losses, DC wiring losses, and this represent the flow chart with a specified percentage, as we see till the power reach the appliances in the home. So in general, if the summation of all these losses represent 40%, as we see, so the system performance of the specified off-grid system will be PR equals 60%. Okay, so all these factors will cause a reduction of power, and finally reduction in the energy that can be used for feeding the appliances in the home. Okay. This table, more details, represent optional value of overall DC to AC derating factor, cause of energy loss, percentage loss, acceptable range, design or operation and maintenance source of losses. As example, module power tolerance, this value 0.95. This is the present acceptable range, and this can happen in both design stage and operation and maintenance stage. Also, module degradation, this value, this is the acceptable range. This table just for more clarifying the sources and the values of the acceptable range. Also, module mismatch, this value, diodes and connections, this value, DC cable losses, AC cable losses, dust and dirty, system downtime, also cause of losses, and shading, reflection, spectral losses, irradiance. The important issue that we must take in our notation while we are making a design calculation, that general system derate factors represent the multiplication of all these factors. It will be equivalent to the final result will be 0.73 percentage. This and about 27 percentage represent the total or the overall DC to AC derating factor, as you see in the next slide. So the adjusted total daily energy required, as we explained in the first slide, that the maximum required continuous AC power equals to 2.325 kilowatt for this example, and the total energy required 21 kilowatt hour per day. So as we see, we are starting our calculation from the appliances or from the home towards the solar modules. So the adjusted total daily energy required after we are taking into our consideration the overall derating factor will be equals to total load consumption kilowatt hour per day multiplied by 1 plus system derate factors. As we see, this value 21 kilowatt hour per day multiplied by 1.27. This represents the derate factors, and the total energy or the adjusted energy required in our calculation will be equal to 26.67 kilowatt hour per day. Okay. Now we are talking about the inverter sizing. As we discussed before, that the DC to AC ratio, which represents the ratio between the nominal power of array system with respect to the AC power of the inverter, or sometimes called inverter load ratio, as we discussed before, or even called array to inverter sizing factor. These parameters in design inverter load ratio or DC to AC ratio equals to power peak power of array in DC divided by the AC power of the inverter, which represents the peak power U.S. Energy and Information Administration state for individual systems that DC to AC ratio, the best value equals to 1.13 to 1.3. This is very good range for taking into consideration while we are making design and calculation of the system. If we assume that the inverter efficiency equal to 97 and the inverter must be greater than by 25 to 30 percentage of the total power required by the all connected appliances that operating simultaneously to compensate the losses of the system. So the inverter power equals total AC power for the load multiplied by the safety factor. If we use this safety factor 1.2 or increasing by 25 percentage, it will be equal 1.25 multiplied by the maximum load, which equal 2325, and the required inverter approximately 4 kilowatt for our system in this case. Okay, as we see. So the continuous power rating, what's this mean? When an inverter is rated at a certain number of watts, this means the continuous power rating for the inverter. The term surge power represents the power to handle instantaneous overload of a few seconds to provide the higher power required to start a certain type of devices and appliances. As general rule, the surge power of the inverter, some references said or told us, must be equals to twice the continuous operating capacity of the load. So, the device that operates without surge power, in our example, for the home appliances were equal to 425 watts. So the total load with surge will be equal 425 watts plus 3605 watts, and this approximately 4 kilowatt, the capacity of inverter that we are required for the safely operation of the appliances in this case design. Okay. So, as we see, in this case, this represents total surge load. Okay. All these movements in order to take your attention while you are making your design. Okay. Now let us select the suitable inverter for this case. Our selection of inverter PV 34 kilowatt type VHM AC power, and a part of this characteristic will be shown in the next slide, and the MPT range at operating voltage in the range of 64 as minimum value of MPPT or maximum power point tracking voltage to 145 volt DC, of course, and the maximum PV array open circuit will be equal to 145 volt DC, and the inverter efficiency 0.97, and the maximum or allowed PV array power for this type of the inverter, equals 5000 watt. I will put this hint. The size of 4 kilowatt was chosen for expanding the load in the future and increasing the number of solar modules, and in order to avoid the replacing the inverter and wasting money. As we see, the total load was less than this value, but if we are putting or planning to increase or the capacity of the photovoltaic system, I choose the capacity of inverter more large in order to avoid replacing the inverter, and if we are replacing the inverter, this represents a wasting of money. This is a part of the critical characteristic of the inverter. As we see, I take my attention upon a solar charger inside the inverter, and the maximum PV array for this type, as we say, 5000 watts, and maximum PV charge current 80 ampere plus minus 4 ampere, and DC voltage 48 volt, and this represents the MPPT range at operating voltage, this value at 48 volt, and maximum PV array of circuit voltage, as we say, 145 volt DC. And this is the end of the second lecture. I hope I will meet you again in the third part. Till that time, I will say for all, thank you for listening and goodbye.